Hey everyone, I am back, picking up where I left off. Sorry about the abrupt ending earlier. I tore my favorite stylus, so sad. So I had to wait till I could get home and get my other ones. So I have a fresh one now. So we're going to pick up where we left off, drawing enantiomers. So I was going to do another non-linear. My kid is talking to me. What?
Warn them about up front,
Uh,
in the waist.
Ironically enough, she was telling me to warn you guys about possible noise from the dogs and interruptions. Kind of funny considering she interrupted, huh? Hilarious. Alright, so, anywho, let's take a look at this one. Alright, so, again, same type of approach, right? What you want to do is find any stereogenic centers that you might have in the molecule, right? This is going to be your only one, not the carbon next to it because it's got two H's, right? So if we wanted to draw our skeletal structure, our enantiomers via skeletal structures, you could do this. And same thing, with the H. If you have an H, you don't necessarily have to draw it. So we have this. If you wanted to draw the H's, that's perfectly fine. They're right there. Okay. Now we can also do this in condensed form, right? So you know what to do. Draw your center, draw two planar lines, draw a dash and wedge. Alright, and then put stuff on it. Alright, again, doesn't matter really in this first arbitrary drawing. Alright, so there's one enantiomer. And here's the second. Voila. Alright, so and I actually talked about this a little bit the other day, a couple of different ways to draw enantiomers. Now, we haven't done this yet with cyclic compounds. Let me show you an example of a cyclic. Now, with cyclic, see, we had one like this. Right? If we had one like that. Now, I'm never going to draw a cyclic in condensed form because it's really a hassle, drawing the rings like this, CH2, 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 etc., etc. Yeah, so forget that. I'm just going to draw skeletal. All right, so again, if we see a stereogenic carbon, stereogenic carbon right over here. So now, be sure, again, draw the reflection. Take note of where the double bond is. If we were treating it like a mirror image, it should be there. And the Cl is right there. Now, in this example, again, that carbon, the stereogenic carbon, also has an H, so we didn't draw it, right? Now, it does change, though. If you have something else on here, let's say, our fourth group, instead of being an H, was a methyl group. Now, if it's something that's not an H, then yeah, you always do have to draw it. So in that case, it would look like this. Okay? All right. So there's lots of good examples in the middle of your chapter and at the end of the chapter. So be sure to work through this. Practice drawing your enantiomers, drawing your mirror images. recognizing where your stereogenic carbons are going to be, and drawing everything three-dimensionally. All right. Now, what we're about to get into shortly is going to be looking at a system, a classification system, to help us tell or sort of assign different names and labels to different enantiomers, right? We said within a pair they look very similar, but they are different, right? Just to illustrate how different they are, we talked about this at the very beginning, how stereochemistry can make two different compounds that are very similar act very differently. Here's a good example, and it's one you may have heard of in one of your biology classes in the past. If you haven't, there's a pretty decent chance you'll talk about it in the future. And that is something called thalidomide. Actually, I think that's an A. Thalidomide. All right. Thalidomide is a drug that was given to pregnant women several decades ago. I want to say, I should have looked up the history of it. I want to say it was back in the 1950s. You may have to double check on that. It was given to pregnant women to treat them for morning sickness, right? Obviously, morning sickness, vomiting, nausea is a common side effect of pregnancy a lot of times. And so this can be very difficult to deal with. So thalidomide was a great anti-nausea medication, and it worked fantastically for morning sickness. However, unfortunately, it turned out that many of these women who took thalidomide ended up giving birth to babies that had severe birth defects, major deformities in limbs, and other abnormalities that were often fatal. So it was very sad. And obviously, once this was discovered, then it was discontinued. It was discontinued for that use. Interesting thing about thalidomide, you can look up the structure of thalidomide. It's got, fairly complex structure. There's actually two different enantiomers of it. All right. There's one type of enantiomer that we call the R enantiomer, and we'll talk about the labeling system in just a second. All right. And there's another one called the S enantiomer. All right. They are enantiomers of each other. They are two separate compounds, right? However, the thalidomide that was being administered to people was actually a mixture of these, right? So it contained both. The R thalidomide, in and of itself, is a very effective sedative and anti-nausea agent. And it is also harmless to, in and of itself, it's harmless to developing fetuses, right? So this is the good thalidomide, so to speak. However, the S form is a severe teratogen. Teratogen is a word that you'll hear when as a warning on the warning label of a lot of different chemical compounds. Teratogen means that it can cause birth defects. All right. So basically, you were getting effects of both enantiomers when this drug was administered to pregnant women. They were feeling the anti-nausea effects of, whoops, I forgot to put nausea up here. They were feeling the anti-nausea effects of the R enantiomer, but also, unfortunately, the teratogenic effects of the S enantiomer. All right. So, it was discontinued for that use. Now, you may wonder, okay, why not just give the R enantiomer without the S enantiomer? And you actually can do that. It is possible to separate these beforehand. Unfortunately, what can happen is when you take R thalidomide, your body will actually interconvert some of it into the S isomer, the S enantiomer, while it's in your body. So no matter, even if you start off with R, you're still going to get a little bit of S. So thalidomide actually is still used in certain applications for this anti-nausea sedative. It can actually have a hypnotic effect in some cases, but only very select administrations. Obviously, no pregnant women. It can be administered to men and also to women who are going to not have any chance of giving birth to a child. All right, so very selected cases. But it's just a really good example, a very drastic example of how just a little difference in stereochemistry can cause big effects. All right. Now, how do we actually label something as R or S? All right, R and S refer to what we call the configuration. Okay, so we are going to learn the system for doing this. The system is very systematic, very step-by-step type of thing. All right, the very first thing that you're going to want to do is assign priorities to the 4 groups that are on your stereogenic center. All right, so you assign them the numbers 1, 2, 3, or 4. 1 equals the highest priority. 4 is lowest. All right? So kind of within this system of RS system, you actually have a subsystem that we have to do first of all to figure out the rules for assigning priority. So here are the priority rules. All right? So the first thing you look at is going to be the first atom of each of the 4 groups directly attached to your stereogenic center. Higher atomic number equals a higher priority. Okay, so let's say we had something like this. Okay? All right, so if we have something like this, we can see that this guy is going to be stereogenic. And if we want to see, I'll just go ahead and draw out that hydrogen that's attached. All right, you can see we have 4 different groups attached. We have an NH2, an H, a Br, and an ethyl group. All right, so what you want to look at the atomic numbers here. All right, so we have a Br, an H, a nitrogen, and from the ethyl group we have a carbon. Which one of those has the highest atomic number? Well, in this case, it's going to be bromine. So the bromine group has highest priority. Nitrogen has the next highest atomic number. Carbon is going to be 3rd, and hydrogen is 4th. Pro tip, if hydrogen is one of your 4 groups, it's always going to be last. Because, hey, you look at the periodic chart, nothing comes before hydrogen, so it's always in the rear if it is one of your 4 groups. Okay? Let's take a look at this one. Actually, I have another rule I want to write before I look at the next one. I did not mean to erase this. There we go. Okay. If there's a tie, keep going down the line. And I'll explain this one in just a second. Alright, so when I say a tie, basically what that means is we have a situation sort of like this. Alright, so in this case, here's our stereogenic carbon. Alright, and so we have a bromine, a chlorine, a methyl group, and an ethyl. Alright, I think the top 2 priorities are pretty easy to identify, right? Br has the highest atomic number. Then we have the Cl. Now, we have a decision to make, right? The methyl group has a carbon attached directly to your stereogenic center. The ethyl group has also a carbon, right? So that's a tie. Well, if you have a tie, like I said, you keep going down the line. What you do is you see what is then attached to that atom. So if we look at this atom, this over here, we can see that this carbon has just 3 other H's to it, attached to it. This carbon has 2 H's, but it also has another carbon, right? the carbon that's attached here supersedes the 3 H's that are attached here. So that means the ethyl group gets 3rd priority, and the methyl group is 4th. Okay? Try another one. All right, if we look here. All right, we have an NH2, an NHCH3, a methyl, and a propyl. All right, we know the 2 nitrogen-containing groups are going to be your highest priorities, right? So, which one, though? Well, we have a tie with nitrogen, so we have to see what else is attached to this nitrogen. The nitrogen on the left has 2 H's attached to it. The nitrogen on the right has 1 H, but also a carbon attached to it. So, it's going to win. That's right. That means this guy's going to be number 2. All right, now we have a CH3 and a propyl group. Again, another tie, but you guys know by now, they keep going down the line. It should be hopefully apparent to you that the propyl will have a higher priority than the methyl. Okay? All right. All right, the next one, to be quite honest, you're probably not going to run into very often, but you might run into it occasionally, so I want to make sure that you're aware of it. All right. First of all, let's review the definition of something called isotopes. You guys have talked about isotopes before in Gen Chem. Just to refresh you, an isotope is going to be an atom that is the same element, but in a heavier form. And it's in a heavier form because it has extra neutrons. All right. Couple of examples, right? Carbon. The usual form, the most abundant form of carbon is carbon-12, right? It has 6 protons and 6 neutrons. But there is a heavier isotope of carbon called carbon-13. It's got 6 protons, just like carbon-12 does, but it has 7 neutrons. Right? Hydrogen is another one, right? Regular hydrogen, or the most abundant hydrogen, is just hydrogen-1, right? 1 proton, no neutrons. You can also have a heavier form of hydrogen, right, that has 1 proton but 1 neutron as well, right? And that is actually called deuterium. And is sometimes represented in structures by the letter D. All right, so if you see the letter D, that stands for deuterium, heavy hydrogen. All right, and I'm going to draw this over here because I have room. You can have even heavier hydrogen. You can have hydrogen that has 1 proton and 2 neutrons. So that's hydrogen-3, also known as tritium. Tritium quite frequently is represented by a T. Okay? So, with that in mind, we can also occasionally see those pop up in structures, and we have to account for them in the priority list, right? A heavier isotope equals higher priority. Now that's only between two elements of the same type, right? So that's only like if you're comparing hydrogen-1 to deuterium. It's not like deuterium's going to have a higher priority than bromine or something like that, right? So just keep it within the element family. Right, so if you had something like this, let's say you had a carbon that had an H, a CH3, a deuterium, and a tritium. All right. Well, the atomic number of D, T, and H are all 1. The atomic number of carbon is 6, right? So the methyl group is going to have highest priority. All right. all the atomic numbers here are the same for the other ones, but they are isotopes. And so what you do is you go by the mass of the isotope. Tritium is the heaviest of these, so it's going to get number 2. Deuterium would be 3, and poor little hydrogen once again brings up the rear. Okay? Like I said, you probably won't run into it that often, but you might run into it occasionally. Alright. The next one is probably the trickiest of these rules to kind of get the hang of. It's not too bad once you get the hang of it, but you might have to practice with it a little bit. Alright. What happens whenever you have double and triple bonds that appear? Alright, you might run into a case where you have a tie between two atoms, but one of them's in a double bond, one of them's not. Alright, well, how do we treat that? Alright, so I'm going to write the rule down, then I'm going to explain it. Alright, if an atom is part of a multiple bond, meaning double or triple bond, treat it as if it had an equivalent number of singly bonded atoms. Now I know what you're thinking. Okay, that was a lot and I still don't understand. Well, let me demonstrate. All right, and people, depending on how well your vision is, so to speak, some people can just look at these and tell immediately what's going on. Other times, people kind of have to use a shortcut or like a little guide, and that's kind of what this rule is. All right, let's say we had something like this. Okay, now this is going to be our stereogenic carbon. All right, so we start looking at the atomic numbers here. We have a Br, a Cl, and then 2 carbon-containing species, right? Well, Br is number 1, Cl is number 2. All right, now, if we look at this, all right, we have a tie between the carbons here and the carbons here. And if you go further down the line, well, we have a carbon attached to another carbon on the right, and we have a carbon attached to another carbon on the left, right? So, is it a tie? It's actually not. What you can do is you can imagine, and I'm just going to redraw this to make it easier to conceptualize. You treat it as if it had an equivalent number of singly bonded atoms, right? We know that this carbon right over here is double bonded to another carbon over here. Right? Instead of drawing that double bond, I'm just going to draw a little imaginary single bond here. Right? Basically illustrating the fact that this carbon has 2 bonds to another carbon, whereas this one only has the 1. And this carbon over here on the far right, this one that I'm tapping over, that's also part of the double bond, so you could draw another imaginary C coming from it as well. So if you look at it that way, then it's a little bit more obvious that this one is going to be higher priority than this one. Okay? Like I said, it takes a little bit of practice, but it's not too bad once you get the hang of it. Let's try another one. I'm going to try to make this one tricky. All right, let's take a look at this one. Stereogenic carbon here. All right. Now, first off, you have, hopefully, you have the ability to see that the two oxygen-containing groups are going to be number one priority, right? Because if you go directly from the stereogenic center, we have an O, we have another O, we have a carbon, we have another carbon, right? So the two oxygen-containing groups are higher priority, right? Now, actually, this double bond never really enters the equation because the O on the left just has another H attached to it, whereas the O on the right has a carbon attached to it. So that means this guy is going to get number one priority, that one's going to get number two. All right. The bottom one's slightly trickier, right? If you look at this, it initially seems like your isopropyl group might have the higher priority because this carbon is only attached to one other carbon, whereas this carbon is attached to two. But don't forget what we do. If we have a carbon in a multiple bond, we're going to treat it as if it's in an equivalent number of singly bonded atoms. So you could sort of think of this one as being more like this. Now you see that this carbon looks like it's attached to three other carbons, whereas this one's only attached to two. So this one's going to be 3, and this one's going to be 4. Now, don't get trapped, though, into the thought process that anything with a double or triple bond is always going to be the higher priority one. All right, you have to look carefully at it. I'm going to tweak the same exact problem just a little bit. Okay, I added an extra carbon here, and that's going to make all the difference. All right, this one's still going to be number 1. This one's still going to be number 2. Now, if we look at this, carbon here, that's a tie. All right, this carbon right here has 2 other carbons directly attached to it. This carbon right over here has only 1 carbon directly attached to it, and 2 H's. Also, this carbon is not part of the triple bond. It's not part of a double bond either. So even though you see a triple bond on the right side, because of this, the isopropyl group actually would have higher priority in this case. All right? So remember to pay close attention when you're going down the line and applying these rules. All right. Okay, so that finishes the priority rules. So it's kind of weird. We were starting a big system here, the RS system, and we had this whole subsystem in it. And the whole subsystem was the first step. So let's go back to this. RS system. All right, so number 1, we just did assign priorities to all your groups. All right. Next, what you want to do is you want to draw your 3D structure. So you got to use dashes and wedges. And what you do is you want to arrange your lowest priority group in the back. Arrange your lowest priority group in the back. All right. So let's say we had this. All right. So we have a carbon that has a methyl, an ethyl, a propyl, and a Cl. All right. Using our rules of priorities, Cl is going to be number 1. Propyl is going to be number 2. Ethyl's 3. And this one over here is 4. All right. So what we want to do is when we draw our first enantiomer, what we want to do is we want to draw this so specifically the lowest group is pointed in the back. That means it's going to be on the dash. So if we're doing this, we could do it like this. Okay? Methyl group pointed in the back. And, then you could just simply draw the mirror image to get the other enantiomer. And I'm going to try to leave this drawing on here because we're going to use this as our first example when trying to figure out how to label it R or S. All right, so I'm going to erase this and sort of work on the top half of the screen. All right, so draw your images like this. Lowest priority group in the back. And next, you want to trace a circle connecting priority groups 1 to 2 to 3. You ignore the fourth priority. That's why you stick it in the back, right? You're trying to stick it in the back to ignore it. So, for example, if we're doing it on the left structure, right, the Cl group's definitely going to be number 1, the propyl group's number 2, and the ethyl group's number 3. Okay? So, we're going to connect the dots here. We're going to trace a circle, and I'm going to put a little arrow there so we know which direction it's going. All right? If your circle goes clockwise, it's in the R configuration. If it goes counterclockwise, it's going to be in the S configuration. All right? So if we look at this one, 1, 2, 3, looks like we're going counterclockwise, so that means the configuration around that center is an S. Let's look at the enantiomer. Can anybody see a mistake I made? Oops! I just realized I did a bad job of drawing that enantiomer. I drew a bad mirror image. Sorry about that. Let me redraw that. See, it can happen to the best of us. Okay. That's better. All right, so let's label these. Now, Cl's going to be 1, propyl's 2, ethyl's 3. Connect the dots, 1, 2, 3, boom. You see that one's going clockwise. So this stereogenic center has an R. Whenever you have a pair of enantiomers, they're always going to have opposite configurations around stereogenic centers. So, in this case, our one stereogenic center in the left compound had an S. That means S configuration. That means the enantiomer, the same carbon in the enantiomer, will have an R configuration. Okay? We could do this. Let's do one in skeletal form, or excuse me, condensed form. CHBrClF. We did this one way back in the beginning of the chapter. Right? So, again, it doesn't actually really matter the way you draw it at the beginning, except for the fact that you want to go ahead, if possible, to put that lowest priority group, which is H here, in the back. The other assignments are arbitrary. And then you just simply, draw the mirror image. All right, so if we want to figure out the configuration, let's see, Br has the highest atomic number, so it's 1, then chlorine, then fluorine. That gives us a counterclockwise circle, so that's an S configuration. What do you think our other one's going to be? Should be R, right? Well, let's see. 1, 2, 3. Circle goes clockwise, and it is indeed R. Very good. All right. Now, the examples I was giving you just then are sort of where you're starting off with a flat structure and you're just sort of drawing all possible enantiomers and then labeling them. Other times, it'll be presented a little differently. You might have a question that gives you a particular structure and it asks you, okay, tell me what configuration this is. And guess what? Oftentimes, they're not nice, and they'll give it to you in in an arrangement that's not as easy to work with. Hypothetically, let's say we had this one, and you were tasked with trying to figure out what the configuration is around that stereogenic carbon. Well, what's the problem here? What's your lowest priority group? It's going to be that hydrogen, right? Is it pointed in the back? No, it's not. It's pointed off to the side in plane. You need it on that dash specifically, right? So, there's a couple of different ways you can go about this, all right? The first thing that you can do is you can practice flipping molecules. And this is one of the harder things to master if you're not very three-dimensionally, gifted. I'm not. It took me lots of practice as an undergrad to sort of get the hang of this. Basically, what you have to do is you have to sort of imagine that you can grab that molecule and pick it up and just sort of turn it around until you get that H pointed in the back. The problem is you got to figure out where everything else is going to be relative to it as well. In this case, just imagine you had an imaginary hand that you could pick up that methyl group, pick up the molecule by that methyl group. And then let's just say you spun it clockwise. You spun it around so that that H that is sticking straight left would swing around to the back. All right, in that case, the CH3 would still be pointed up. You're going to swing that H around to the back here. Now, what happens to the Br as you're spinning this counterclockwise? Well, that Br is going to spin as well. It's going to spin over to the side, and your OH is going to spin forward from the back. And it's going to look like this. This is the exact same molecule as the first structure I drew, but I've just taken it and spun it around. I'm basically like I'm looking at it from a different angle. And now we have the correct arrangement of the lowest priority group, so we can get about our business. Br has highest priority, followed by OH, then methyl. We have a counterclockwise circle, so that one has an S configuration. Okay? Now, thinking to myself, give me a second. Let's try another one. Let's say you had this. I had to pause because I lost my place on my note sheet, so I was trying to stall. Hashtag teacher secrets. All right. All right, here's another one. All right. So again, we've got the lowest priority group sitting in the wrong spot. So you have to try to three-dimensionally rotate this molecule around in a way to get it into the right form. In this case, this is another one where you can just sort of pick it up and spin it, right? If you spun this one a little bit counterclockwise, that H could swing from the front to the back. That isopropyl group would swing from the side over to the front. And that ethyl group would swing from the back to the side. So again, same molecule, we've just got it written differently now. And now we're able to label and connect the dots. 1, 2, 3. That one's R. Okay? like I said, this takes a lot of practice if you're not naturally inclined. So there's definitely work through a lot of the problems in your book. This is also where having a molecular model kit is super, super, super helpful. All right, so I definitely encourage you to use a kit as you're working with this. I also let you bring in kits on exams just to remind you if you decide to get one. All right, so that's one way you could go about it. There is another way, and I suspect you'll like this. There is a shortcut. All right. Number one, take a given structure. If it's not in the right alignment, right? If you don't have the lowest priority group in the back, you swap your lowest priority group with whatever is on your dash. All right. So let's take that same one we just did. All right. We're going to double check it. We're going to double check the answer using the shortcut method. Now, in this case, that's supposed to be a 3. This stylus isn't as good as the other one. I'm sad. All right, so in this case, our lowest priority group is H. So what we want to do is we want to switch that H with whatever group is on the dash. In this case, that's going to be an ethyl group. So we're going to do that, and we're going to redraw it. Okay? And then we can go about our business, right? We got the H in the right spot. We have a 1, isopropyl's 2, ethyl's 3, counterclockwise, so that gives us an S. But wait a minute, that's not the answer that we got when we did this just a minute ago. Well, keep in mind, this redrawing right over here is not the same as this. We had to break bonds to redraw it like this. All right? So that leads to the second rule of the shortcut. After you do your swap and you get an answer, take the opposite of the answer that you got. All right? Works every time. So doing it this way, doing the shortcut gave us S, so our official answer would be R, which matches up with what we got when we did molecule flipping. All right, I'm going to stop there. The RS system is one that takes a bit of practice and getting used to, so work on it for a bit. If you have any questions, let me know. Now that you know through how to do RS, you can probably do a little bit more of the homework. So I will post the sapling homework up, and you can get started on it as well. Until then, have a good day.